Hello, here is our recorded review for our latest chapter, all over minimization, maximization, or what we can sum up maybe by calling extreme values. So first of all, what are extrema or extreme values? Well, they come in two forms. Sometimes when we're looking at a function, there is the greatest that the greatest output the function ever has, or maybe the lowest output that the function ever has. And we could say across the entire function globally that that is the greatest absolute maximum or minimum value. So if I can spell correctly, we have globally or absolute, well, global or absolute, max or min. Well, sometimes maybe not the greatest that the function will ever be, but in an area around maybe some specific point, it might locally be the smallest value. So we have a local or relative max or min. And there is a really good picture that I like to draw. We are looking at this graph, and maybe our function looks something like this. I've drawn this one a few times. So we can kind of look at this and tell that, oh, there is an absolute minimum value right here. This is the lowest that the function will ever go. So I can call this a global min because it is the lowest that the function ever gets. However, there are some spots in the function that do correspond to maybe a local maximum or a local minimum. The idea is that maybe think of it like a mountain range, or if we're thinking of it in geographic terms, that there are valleys and then there are the deepest valleys, and there might be peaks of a mountain, and there might be the highest peak ever. So each function may have something like this, where we have some points that are, we drop down and then we go up and then we drop down again. But we may or may not have a point that is the absolute lowest that the function will ever go. And this is a good example to show, yes, in this example, there is a global minimum. This is the lowest the function ever goes, right? Because anything else, anywhere else we see the function is somewhere above that. Well, against that, we have local extreme values. So I will call this a local minimum. Well, why just local? Well, if we pretend that we cut everything else out and we just almost zoomed in on this yellow square, then this yellow square would look, if I'm drawing this is like a picture of what I'm zooming in on, this yellow square would look like this. And if we're only looking at this specific spot, then yeah, this looks like a minimum value. And so sometimes we want to care about that. So if we just zoomed in on this picture, this looks like a minimum value. And certainly it is true that in this yellow box that I drew, that is the smallest value, and we care about those. But we clarify that they are locally a minimum, just as this value that I pointed out up here on the top of this hill would be a local max. It is not the biggest the function will ever get, but in this small area, it is. If I restrict myself to just looking at this hill, then yes, that looks like a maximum value. That is the largest value that we get in that really specific area that I cropped out there. So because it is the maximum value for where it's at, it is the maximum value in the area surrounding itself. We call that local, as in around, where you're at. So like in the same world as like we think of local, like around the city, around where you're at, in the very small regional area. So in the area around this point, it is the max. However, we can compare those to the global minimum. Again, this is the lowest that the function will ever go. This function that I drew has that as the lowest point. Now, this is a good time to point out, even though this is a local maximum, it is not a global maximum. And it turns out there is no global maximum in this example. Why? Well, we see here our arrows, our function, or sorry, these arrows here for a function are saying that our function is just going up forever and ever. There is no value that I could pick that is the greatest value the function will ever achieve. If I were to tell you any given number, you can pick a number higher than that this function is going to. So if I said, well, what if my maximum is 5 million? Well, these arrows are going up. We can talk about unbounded end behavior like we did in the first section. These arrows are going up. They are increasing without limit. So even just over here, we are higher than this local max right here. We don't even have to go that far out, but we definitely can. So in this case, we can tell that there is no global maximum, only a local maximum. But it is, I think, a good demonstration of kind of this picture where a function can have multiple mins and maxes, local mins and maxes. It might have one of them turn out to be a global minimum, and even though we may have a local max, we do not have a global max. So this is a really good example that kind of encapsulate all the different cases that we have here. Well, next we want to introduce the idea of a critical value. So let me write critical value. So what's going on here is that we are trying to describe maybe some of the behavior. How can we figure out where these extreme values are, where our local mins and maxes are? Well, if we look at this picture, if we look at this drawing, y'all are really good at pointing out that if I were to zoom in to maybe my local max again, and we draw something like this, and that dot up there. Y'all were really good at pointing out if I said, okay, as we're going along this path, right here, we are increasing, so our derivative should be positive. And over here, our function is decreasing. So if I look at this point, my derivative should be negative. We are decreasing. But at this peak, right at the top, we're not really increasing or decreasing. And it turns out that our derivative is 0. Well, that is exactly the idea of a flat tangent line. So if I were to, be drawing those tangent lines along that shape, it should be flat. And certainly that is something that we get at every local extreme value. So here at this local minimum, we have a flat tangent line. At this local max, we have a flat tangent line. Even at the global minimum, we have a flat tangent line. So what if I want to figure out some way of pointing out where all of my flat tangent lines are so that maybe I can figure out where my max and mins might be? Well, that is where the critical value comes into play. So I'm going to erase this. Our critical values are all the points where our derivative is equal to 0. So we say if f prime of some number c is a critical value. Sorry, really it goes both directions, but I meant to say it the other way. If f prime of c is equal to 0, then we say c is a critical value. And we call the critical point corresponding to this, of course. It is at c, that is the x value, that is our input, that is the x value. Then that point, what we'd call a critical point, is just that x value and its output. So again, this is just the format of a point, an x, comma y, where your x is your input, your y is your output, and here your input is just going to be c. And our output is just going to be whatever value we get when we put this in. So we say c, comma f is a critical point. And that output should be a local max or a local min. Well, how do we know it's a local and not a global? Well, it turns out that really that kind of distinction doesn't really exist. I'm being careful with my language. What I'm saying is that it is going to be the largest value in its local area. It may turn out to also be a global max or min. It may be an absolute extreme value, but we don't know that for sure. And the only way to know that is to look at a greater picture of the function. You'd really have to look at the graph of the function to know that for sure. So oftentimes maybe we don't make that great of a distinction, and we really only look for absolute global max and mins by looking at a graph instead of just looking at stuff like this with the equations. So this is kind of where that distinction comes from, is that our local max and mins are more of a guarantee, should be, coming from our critical values. And it may turn out to also be an absolute global extreme, but we're not confident if that is the case yet. And you're never going to be able to tell unless you look at the function as a whole. Well, how do we know for sure whether a function has a maximum or a minimum? And this is what we get into with what we call the first derivative test. And this first derivative test has three cases. So I am going to maybe draw the first case, but first of all, we're going to clarify that our first derivative test only applies if c is a critical value. So we're going to start out and say if c is a critical value for our function for f of x. So if c is a critical value for f of x, well, let's look at a case that we may have. What if we are looking at some graph of a function that looks like this? Well, like what we talked about before, we can kind of look and we know, okay, this should be a local maximum at least. There should be a critical value right here. The derivative is 0. Well, we are increasing over here, so the derivative should be positive, and then our derivative is 0 at our critical point, at our critical value, and then we start decreasing here. And that would mean our derivative is negative. Well, anytime we have a derivative that is positive, 0, then negative, it would have to make this shape exactly, right? If my derivative is positive, I'm increasing, and then it goes to 0, so I flatten out, and then my derivative is negative, so I must decrease. Then we make this shape. Well, the peak of this shape is always going to be a maximum. So we say our first derivative test, this first case is this picture I drew. If f prime of x, our derivative, changes from positive to negative at c, then f of c, our output for c, our y value, is a local, and we can look right here, that is the top of a hill, so it is a local max. Well, let's consider the other case. What if instead our derivative is negative, so we are decreasing, and then our derivative becomes 0, then our derivative is positive. Well, then we are decreasing, then 0, and then increasing, which means down here, for a critical value down there, that is the bottom of a valley, which would mean that is a local minimum. So if f prime of x changes from negative to positive at c, then f of c is a local minimum instead. So this first derivative test gives us a means of checking whether or not our critical value or critical point is corresponding to a maximum or a minimum by just looking at the behavior of the derivative around c. Well, there is obviously a third case that I have not given the description for. So what if, essentially, imagine our derivative was positive, going up, going up, going up, and then it went to 0. But then it was positive again, and our function continued to increase. Now, this, as maybe feels deceptive, is actually a relatively common graph. This is the graph of x to the third. It has this very silly behavior of having a critical point at 0. However, it is not a local max or min. When we look at this value, this is not the top of a hill, because to the right we just keep going up. This is not the bottom of a valley, because to the left we keep going down. It is not an extreme value at all. However, it still would look like a critical value because our function kind of does go flat right there. And so this is the third case for a first derivative test, and why we emphasize that a critical point should correspond to a local min-or-max, because sometimes it doesn't. So if f prime of x does not change sign, si, that's gn, not sing, sign at c, then f of c is nothing. Technically, it is still a critical value, but it becomes, or critical point at least, but it becomes relatively worthless because it no longer corresponds to any extreme value. It does not mean anything. It is not special. I don't like being so mean to the critical point, but we get what I'm saying. It becomes not really worth our consideration, right? Because again, if we look at this graph of x to the third, Yeah, it's kind of interesting. It is actually, it turns out, what we will call an inflection point, but it is not something that tells us any minimum or maximum value for a function. So we don't care about them at that point. So again, this is why we emphasize it should be a local min or max, because there are points like this on occasion where the tangent line certainly is flat, but there is no min or max value there. And this is again a very specific kind of function. This does not come up a lot because the kind of questions that I ask are not going to be trick questions where this happens. But as far as the grand scheme of functions go, this is relatively common enough to be a fact that we need to look out for. So I am going to pause this video here to make sure that I'm overloading too much information into one video.